Hey, it's Mr. Shrum, and I am back again with a tutorial walkthrough. Last time we were introduced to waves. Now we're going to look at their characteristics in this tutorial. We're going to be able to describe waves in terms of their fundamental characteristics, like velocity, wavelength, frequency, period, amplitude, and phase. So hopefully you will understand all of those words at the end of this lesson. Getting into the intro, Tanya is all set to begin surfing, which is her favorite sport. She sits on her board waiting for the right wave to come her way. One that's neither too big nor too small, but just the right height, like Goldilocks. What will happen if Tanya happens to miss a wave? When will the next perfect wave reach her? If she's a good surfer, she probably has an understanding of wave dynamics. By making a few basic observations and using a little math, she can estimate when the next wave will be, and possibly even if it's approximate height and shape. In this lesson, we're going to explore velocity, frequency, wavelength, and amplitude, like we said earlier, and how they relate to waves. And whether they're ocean waves like Tanya or ultraviolet waves from the sun, all of the characteristics are the same. So first, we are talking about periodic wave properties. What happens when raindrops fall on a puddle? The drops produce mild waves or ripples on still water. These waves are called periodic waves because the pattern of the wave is continuous and repeats after a specific time interval. So there's a pattern and it repeats. So each wave will be periodically coming again and again. Periodic waves are produced by sources that either vibrate or oscillate. Oscillate is another word for wave, like a back and forth motion. In the case of the puddle, the raindrops fall on a particular area of still water and causes a repeated undulation. Undulation is movement at the point of impact, and this generates periodic waves that expand outward, and you can see that here. So a raindrop hits here, and then it will send ripples in a circular motion outward. Another example of periodic waves is that of waves produced by a two-pronged acoustic instrument called a tuning fork. If you strike a tuning fork, the individual prongs vibrate and they create a periodic sound wave in the air. So now we have a lesson activity, a simulation wave on a string. It looks like this. And here are the answers for that. Wave 1, wave 2, wave 3, height from rest position, depth from rest position. From the simulation readings, what do you observe? The readings show that the heights and the depths of all the waves are equal. Now it asks you to reduce the amplitude to 25 and observe what happens, and then increase the amplitude to 90. And when the amplitude is reduced to 25, the height of the wave decreases. When the amplitude is increased to 90, the height of the wave increases. Then it asks you to reduce the frequency and then observe what happens, and then increase the frequency. If you decrease the frequency, the number of waves generated per second decreases. If you increase the frequency, there are more waves forming in the same amount of time. The waves are more frequent. Think of it that way. It seems that the length of each wave gets smaller, but waves are generated more often. And we're going to explain why here. So in this diagram, it shows a periodic wave. The wave starts from the rest line, 0.0, so right here, reaches the highest point at P, and then passes through the rest line again. It continues to the lowest point, and then it comes back to the resting point at Q. So it goes woo, woo, woo. So O to P, to low to Q. All right. The wave has made one complete cycle, and that's going to repeat again and again. So this up, down, back to rest is one cycle. The time taken to complete one cycle is called the period of the wave, and we call that T. So the time it takes to go from here all the way to here, that is the period, T. And we measure that in seconds. So think of time, T, period, seconds. The highest point of the wave is called the crest. So we call this the crest. Points P and R represent two crests in consecutive cycles of the wave. This is one and then two cycles. The lowest point is called a trough. We have a crest up here and a trough down here. This midline, or the rest line, is also known as the equilibrium position. And in the simulation, you may notice that changing the frequency of the wave changes how often waves are generated. The frequency of a wave refers to the number of complete cycles made per unit of time, usually in seconds. We denote that by F, and we measure that in hertz. And hertz is an inverse second. So we'll talk about that in a bit. One cycle or wave per second is 1 hertz. So if a wave completes 5 cycles in 1 second, it has a frequency of 5 hertz. The distance from the equilibrium to a crest or a trough is the amplitude of the wave. So from the equilibrium to the top of a crest, or the top of a trough, or the bottom of a trough, I should say, that's the amplitude. Like, what's the highest point away from the equilibrium point? Wavelength is the distance between any 2 points, one full cycle apart. So you see how this crest is measured to this crest. That's one wavelength. You could also do from here to here, and that's the same distance. For example, the distance between 2 consecutive crests is 1 wavelength. Wavelength is represented by the Greek letter lambda. This fancy Greek letter means wavelength. So if we look at the positions of letters A, B, and C, point A and B are placed on 2 crests. Point C is at a trough. Any 2 points on the wave are said to be in phase when there are 1 or more whole wavelengths or whole cycles away from each other. If you think of a cycle as a trip around a circle, in phase points are, they have the same angular measure. Their difference is 0 degrees. So what does that mean? If we look at point A and B, they're 1 wavelength away, so they are in phase. Point C is out of phase from both of these points by 180 degrees. It's exactly half a circle away from the other 2 points. In fact, any 2 crests or any 2 troughs are always in phase, while a crest and a trough are always 180 degrees out of phase. So these crests are in phase, these troughs are in phase with each other, but this crest and trough, they're out of phase, and these are out of phase. So crest and crest, or trough and trough for in phase, and then crest, trough, trough, crest, out of phase. So what does the term wavelength refer to? Let's test your understanding. It's the distance between two consecutive crests or troughs. So consecutive means the next one. All right. If a wave takes half a second to complete one cycle, which characteristic of the wave does this description represent? Period is the time it takes to complete one cycle in the wave's period. Period and frequency. Recall that the period of a wave is the time taken by the wave to complete one cycle. The frequency of a wave, on the other hand, is the number of cycles completed per unit time. And the unit of measurement for period is seconds, and the unit for frequency is hertz. And we'll look at how these are interrelated. So it takes you on another lesson activity. Wave on a string. It tells you the instructions. And then you are writing down your findings. Period and frequency are inversely proportional to each other. So what does that mean? That means if there's an increase in one, that means the other decreases. And if there's a decrease in one, that means the other increases. So they're doing the opposite, inversely proportional. So let's look. Together, the diagrams shown here, represent the completion of one wave cycle. The time it takes to complete this cycle is the period of the wave. P is a point on the wave generated when the source oscillates. As the source oscillates, there will be a change in the position of P. The frequency of the wave is the number of waves generated per second. So we know that the frequency of a wave is equal to the frequency of its source. If the source oscillates 20 times per second, the frequency of the wave will be 20 hertz, or 20 wave cycles per second. From the simulation, you may have realized that the frequency and the period of a wave are the inverse of each other. And in mathematical terms, this is what that means. As T gets bigger, F has to get smaller. And as F gets bigger, T has to get smaller. And that is how you describe this relationship in math. If you ever see one variable equal to 1 over another variable, that is an inversely proportional relationship. So let's look at an actual example. Problem: the musical note has a frequency of 440 hertz. What is the period for this sound wave? So we know that the frequency F is 440 hertz, excuse me. And we know that its period is given by T equals 1 divided by F. Well, if we know F is 440, we have 1 over 440, and that equals 2.27 times 10 to the negative third power. So the period of the wave is 2.27 times 10 to the negative third power seconds. So that's 0.000227 in another way. So it's very quick for them to do one cycle. So enter the variable symbol for the quantity you need to. So the period is t. We're given the frequency of a radio station, 89.3 megahertz. And we know that this equation, the period is equal to 1 over the frequency. So we already have the frequency. And we can just plug it in. 1 divided by 8.93 times 10 to the 7th power. And that's it. And this is because this mega is another way to say times 10 to the 6th power. So that mega, oh, come on, oh, there we go. That is equal to 1 times 10 to the 6th power. Oh, sorry. So let me just do 10 to the 6th, okay? So if you have 89.3 megahertz, you're gonna have to, you have 89.3. Well, we like scientific notation, so you're gonna move that decimal over one space, 80.93. And since you moved it over one space, you'll have to add power. So that is all 10 times to the 7th power. Because you moved that one space over. But this is the same as this. Okay. Mega is just multiplying it by 10 to the 6th power. And then if you wanted to move this decimal place over, so you had 8.93 times 10 to the 7th. And that is the same thing. I'll put both. Try it out, put it on your calculator, see what you get. You should get the same thing. So that is all that is. And we'll probably go over that briefly in the next mastery test lesson too. But moving on, we have the amplitude and energy. Remember that the amplitude of a wave is the distance from the equilibrium to the crest or to the trough of a wave. A wave is generated when energy is transferred from the source of its surrounding matter molecules. And for example, water waves are generated by wind. The energy from wind is transferred to some of the water molecules, and that in turn transfers energy to the molecules next to them, and that generates a wave. That's getting the water moving. The amplitude of a wave depends on the amount of energy transmitted by the source. So a strong wind blowing for a long time may generate large, very high amplitude ocean waves, but a more gentle breeze may only make mild or very low ripples in the water. Waves that have high amplitudes, so the higher the waves, transfer more energy. High amplitude waves may carry enough energy to lash at a boat and turn it over, while small ripples may only be able to move lightweight objects like shells or seaweed. And then it brings you back again to an activity. So I'll show you the answers to that. You're messing with the damping force and measuring the amplitude of waves. And what is the conclusion? Well, you're introduced to the idea of a damping force. And if you increase that damping force, the amplitude of the next waves decrease. And the more damping force there is, the faster the amplitude decreases as the wave travels. So waves may be initially very high, and then energy is lost over time due to a damping force. And we'll learn that in the next few slides. So think of this. So first wave's big, and then less big, less big, less big, less big, until there's not really any wave left. It's like when you jump into a pool, the water around you may splash very much, but then once it reaches the edge of the pool, the waves aren't very big at all. The damping force decreases the amplitude over time, and that's because it diminishes the energy being transferred through the waves. So from wave to wave, there's less energy being transferred. When a wave is generated, particles of the wave carry the energy to other particles in a chain. It's like a chain. But if there's an external damping force acting on the particles, energy is lowered, reduced. So the next particle in the chain receives less energy, decreasing the amplitude. And that's a lot of the real world situations. Gravity, friction, damping force, you name it, that opposes the motion of the wave. For a high amplitude wave to be transmitted a long distance, the source must provide high energy and the external damping force must be very low. What will happen to a periodic wave acted upon by an external damping force? Like we said, damping force dampens the amplitude. It lowers the amplitude of the wave. So in summary, if you remember Tanya surfing in the introduction, she was looking for the right wave to surf. And for surfers to get the best experience, they need to understand what's going on with the waves. There is a physics and a mathematical way to go about things. And if you know a little bit about the period, the frequency, amplitude, and the wavelength of waves, that can help you in your surfing journey. Ocean waves are periodic waves. They repeat a fixed pattern over time. The period of a wave is the time in seconds it takes to complete one whole cycle. Frequency is the number of completed cycles per second. So period and frequency are reciprocals of each other. They are inversely proportional. At any location, waves might be converging from more than one direction. So surfers must time waves mentally to determine the basic period at any given location. Amplitude is the distance between the equilibrium and a crest or a trough of a wave. Surfers look for very large, high amplitude waves because they have more energy, and surfers can go faster and they can travel farther on a big wave. It's possible for two or more waves to converge from different directions, and they'll double up on each other. So surfers will often look for a pattern of big and small waves. For instance, every seventh wave might be especially large. A damping force on a wave is an external force that decreases the wave's amplitude. When waves with high amplitude are acted upon by an external damping force, they transfer less energy and decrease the wave's amplitude as it moves along. Shallow spots away from the shore can damp the wave amplitude and also slow the wave motion. Tanya, who is waiting for a good wave, will have to decide in a split second whether an approaching wave is the one to go for. A little practical physics knowledge can go a long way if you decide to surf. And you can click here to learn more about the physics of surfing. It talks about the joy of surfing, the joy of physics, and you don't need to whip out a calculator, right? Just with a little bit of knowledge, you can use it to your advantage. And it talks about gravity, the buoyancy, the net force, balance, a lot of interesting stuff. Force diagrams. Always remember to draw force diagrams. And it actually gets really into depth, why surfing works the way it does. Hydrodynamic forces, wave breaks. Yeah, you eventually will have to stop surfing. So people fall off or bail. But yeah, that's cool. Look how old it is. Maybe 2003. Oh, wow, that's crazy. And that's the end of wave characteristics. So congratulations. And I will see you next time to talk more about waves and physics and physical science. So until then, enjoy the rest of your day/week and stay safe and warm. Bye-bye.